Hello guys, this is Ravi Rajput. Welcome to my YouTube channel NextGen Neuron. So today we are going to discuss the internal mechanism of any AI model. What is the internal process of any AI model it goes through, right? Either that is RNN or that's a CNN or it's a transformer, right? So any kind of model like advanced and basic. So it goes through certain step, or you can say it's life cycle steps, right? Look, we are going to discuss that in detail, what those steps are and what is the purpose of that thing, right? Every AI model goes through like same certain steps, which we'll discuss. The first step is preparing the data set or collecting the data, because you definitely need uh, good quality data and meaningful data if you are going to train your model on it, right? Data, quality data is the first prerequisite. The second thing is splitting up that data into training and validation. Why we do that thing, I will also explain that. And third step, maybe you are doing the training of that model on the training data set, and then you are doing the validation and and how those accuracy and loss are captured. So we'll discuss everything in detail. I'll tell you the purpose of each step, and that will make you much clear what that neural networks algorithm is all about, or what that process is all about, right? So you'll get a good understanding what that AI training is all about. So what's the purpose of that, I mean to say. Let's discuss it, guys. As I mentioned, the steps are going to be same for any type of model, like for image thing, like for the CNN or for the RNN or for transformers, what we discussed, right? Or even if you consider way beyond, like uh, the image generation, which is a Gen AI kind of thing going on, right? The diffusion model. All the models are going to have, or even the simplest one, which is a feed forward neural network, right? Which we'll discuss here. Every model is going to have the same process. So what I have done here, I have used feed forward neural network to explain these things, because that is known as the simplest form of neural network. So you don't need to deal with multiple or internal complexities of the model. It's just a very simple thing, right? So it's a very simple architecture, as well as way easy to understand. That's why I had opted feed forward neural network to explain this training and validation process. Okay, so let's go one by one. First, as I had explained before, or you can understand, I'm just trying to install the PyTorch here. Okay, so PyTorch is a framework, a deep learning framework, which is definitely a number one framework nowadays. Everyone using it, right? So I had also used a PyTorch. So it's based on Python. So definitely you need Python knowledge, some level of knowledge, and programming language understanding, like Python programming language understanding specifically, if you are dealing with these frameworks, either TensorFlow or PyTorch. Okay, so the first step is installing the PyTorch. So it will take few moments or few seconds to connect with my GPU, and it will install the PyTorch. So yeah, so it's connected and installing it. You can see it's downloading the PyTorch in my Google Colab runtime. Okay. Meantime it is happening. I'll show you the later steps where I had, what I have used. I have simply imported the required packages here for the PyTorch packages, as well as the dataset which I'm going to use here is a California housing. So guys, what I had tried to do here, it's a very simple neural network going to do a very simple task, and that is a house prediction. Like based on the features of house, or like there are certain features like medium in MEDINCL. I think that should be median of income, something like that. House age, average rooms, bedrooms, so population in the area. So these are the features which defines the cost of the house in that area, right? So we have a large data set that is called California housing data set. So based on the features of a house, right, or the location or population of the area in which that house is, right, we have defined the price of that house. So based on that learning, model will try to predict the price of house for any unknown feature data, right? So any unknown feature, it will try to predict what should be the, so if you give any specific feature, yeah, these are the number of bedrooms, or these are the and this is the population, this is the location where the house is situated, tell me the price, right? So model will give you the price based on its learning. So that's what we are going to do here, right? So we are going to use the California housing data set to train the model how to predict the prices of a house based on its features. Okay, so that's still going on, guys. I think that's done. So it is done. Yeah. So the torch has the PyTorch has been installed, and another package I had installed is scikit-learn, which is having some neural networks library, right? So like the housing data set and test trainer split functions. We, for those for yeah, using those, we need to import the scikit-learn library as well. So once those two things are done, PyTorch and scikit-learn has been installed. Now the third part is you can see I have imported the required packages here, like the PyTorch as well as the neural network model of PyTorch, and Optim will discuss what that is about, right? And definitely the data which we need, right? So this is a pre-built data set available in scikit-learn library, that is fetch California housing data set, which we'll use to train our model. And yeah, so test train split function, which is used to split the data set into two parts for training and testing. Standard scaler may not be used, or you can use it to normalize your data. And yeah, and another one is tensor data set data loader. I'll explain below what that is about, and matplotlib to plot the graph. This I might have not used here, but just imported. But I'll let you know what is the use of this particular package as well, right? Okay, so the first is definitely loading the data set is the first step which you need to do, right, as a part of the process. So data set, either you are using a custom data or you are using any pre-built data. There are many data sets available on internet which you can use to train your model. Okay, so I had load the pre-built California housing data set, and as a part of next step, what I had done, so data set is having features and predictions, right? So the x is the data and y is the result, like the 13 features or 8 features or 13 features, I think 8 features are there, right? So all these features are, like the input features are the part of x, and the output, like the prediction of the house, is the part of y, right? So for example, you have a data set, house age, average rooms, average bedrooms, the cost is this. House age, average bedrooms, population, the cost is this, right? So the features are going, the input features which you are going to put, that is going to be x, and the output, the prediction, that's the answer, right? So the prediction is going to be the part of variable y. Okay, so that's what we have done here. So x is having all the data points, as and y is having the target or the output value. So now let's print what this California housing data set is having in it, right? So yeah, 8 features are there. Okay, now as I mentioned, like you can optionally you can normalize your features as well. It's good for you. And the next thing is next thing comes is the test train split. Okay, so test train split is an important thing. So what this function does, it will split your entire data set in two parts, like for testing and for training. So I might have explained in my previous videos. So if there is 100% of data, right, so usually 80% of data you keep for training the model, and learn, and rest 20% you use to test the model what it has learned during the training, right? So this is a strategy. So the much data you will use for training, the much it will be good for a model, right? So you are giving, like, obviously you are giving the model more data to learn, right? And then you're testing. So usually the ideal ratio is 80-20. It, like 80% of data you can use for training, and then you will do the validation on 20% of data set. So here the same thing I have done. Like it has a 80-20 ratio, the test size is 20%. So rest 80%, the features of the rest 80% data will go in xtrain, and um, and yeah, and this for rest, and 20% of the validation data features will go in xtext, xtest. Ytrain should be having the predicted values for the training data, and ytest should be having the predicted values of test data. So if you're combining all these xtrain, xtest, ytrain, ytest, it's going to form a full data set. Yeah, okay, whatever you have downloaded. So this is the reason of splitting it. Random seed, definitely for reproducibility. I had explained my previous videos as well. So we use random seed. So if you are doing the training multiple times for the model, so it should not randomly pick any data point, and because if you are not selecting the random seed here, right? So for every training it will learn differently, different patterns may have some different results, right? So if you want the consistency of the model throughout the training, number of trainings you are doing, right? 1 2 3 4, so it should give you the same result. That's why we use random state. So it's for reproducibility purposes. Okay, let me execute it. So yeah, that's done. So testing and training split has been done. And yeah, data set has been divided in two parts. Another one is convert to tensor. So definitely, guys, so you have to convert in the tensors, right? So you cannot use straightforward the data what's available, right? You just need to convert in the specific data type which your PyTorch understand, right? So that's why, like, so the PyTorch understand the data type as, like, yeah, so your PyTorch understand your data as tensors, right? So we can discuss more about the tensor, what the tensors are. It's a basic unit of neural network, right? So the data which whatever you are providing to model, it should be in the form of tensor. So this is just a conversion of the actual data set into a tensor. Okay, and the next step which it comes is the data loader. So once the data has been converted into the tensor, right? So once the conversion have been done, the next step comes is loading the data into the data loader. So data loader is an element of PyTorch which holds the data, right? And configure some internal batch sizes, and like whatever the internal mechanism suitable for PyTorch, right? So that is basically those are done in the data loader. So yeah, you can understand more what data loader is. So the data loader, basically you are just putting the data inside your data loader, and it's a kind of wrapper, and you are using that data loader to train your model. Okay, you are giving the batch size here, shuffle true, like it will keep on shuffling the data internally when the model is going through the intense training. Okay, so that comes as a train loader. So in PyTorch you can directly give the data set for training. You just need to put in the data loader which you will take ahead for training purpose. Okay, so here what I have done, I have just put my data into the data loader object to make it training ready. And the next is the important. So guys, this is a regression model because we are doing the prediction here. So prediction usually are called regression model, regression process, right? So if you are doing some prediction, there are two things, right? Classification and prediction. So classification is classifying the data points into multiple classes, what we had done in our sentiment analysis, as well as in CNN, CNN video as well, right? So that was an example of classification. But this is regression. It means you are predicting the value. You are not classifying, so that the output is being predicted here. You are predicting the house price. So that's a regression model. Okay, so let me explain this model. It's a very simple architecture. This is the specification of PyTorch, how you define your model. So the regression model of class I had created, I'm passing the module parameter here, yeah, module class. And yeah, so here I had used a simple sequential layer, NN layer, right? Yeah, sequential layer I had used, in which I'm using linear layer as well as along with the ReLU input. So this is also the similar. Like what I had done, I had used the two pairs of linear layer as well as ReLU function, activation function. So not more than that. So it's a pretty simple model architecture, guys. Right. So you can understand how it is defined. You can have n number of layers in it, right? But it will increase the complexity. It will take, more consumption of your resources. The model will be complex. It may go overfit as well, right? So if you are doing randomly increasing the number of layers, so you just need to tweak it based on some best engineering practices, and you need to give the optimized value here. Okay, so here I had given the linear layer ReLU function as well as one more pair of linear and ReLU function. So I had mentioned it 13, it should be 8, okay, because there are 8 input features we discussed, and 128 neurons. So in the second layer, all those 128 neurons are connected to, are the input for the next layer, like 128 neurons, and the output are 64. 64 neurons are going to be the output of second layer, and in the last the 64 inputs, and one should be the one neuron should be in the output, which will be giving your product predicted house price value. Okay, so this I'm executing, the model has been defined here, and the next part is I'm initializing this model, whatever the class I had defined. So I'm initiating this this regression model, and guys, this is a loss function. Okay, so the loss function is basically I had this is again another step of neural network process. Like after that, right? So what that loss function is, it gives you how much accurate your model is. Okay, so if after each iteration, model will calculate the loss. How the loss is calculated, it will compare the predicted value and the actual value, whatever is in the data set. If the both the values are same, it is correct, loss is zero. But if there is a great difference, it means it is not correct and the loss is high. So loss is a kind of correction. Okay, so uh, uh, yeah, so loss, there are different type of loss functions available in neural network. If you want to understand, you can simply go to my another website, styrisci.com. So here I had explained about these loss functions. There are different type of loss functions. Okay, so optimizers and loss function, go through this page, you will get a decent idea what that loss functions are and optimizers are. Okay, so loss function, there are different type of error calculation, like mean squared error, where you are going to calculate the average of square of all the errors. Like this is the predicted value, actual value, we calculate the difference, that square, and we are calculating the average for all the data points. Okay, so number of examples in data set. Similarly, mean absolute error as well, right? So instead of doing the square, we are just calculating the absolute value and the average of it. Binary cross entropy is um, another method of calculating the error. Categorical cross entropy, CCE. So there are various loss calculation methods available in neural network. So you just need to use that based on your necessity. Okay, so but here we have, since this is a regression model, I have used the most suitable error method, that is mean squared error loss here, right? I also told what the loss is about. You do the prediction, you compare the output with the actual output. If there is a great difference, the loss is high. If the values are equal or correct, the loss is zero. Okay, optimizer is another element which you use to optimize the neural network process, like updating the weights and calculating the gradients, which I'll explain what that is about. And defining the learning rate, which I had. So this is the learning rate based on what the model will be learning. Okay, so it should be relatively slower. The slower learning rate means model is, step taking the slower steps to learn or to go through the process. Okay, if this is high, model will jump, like it will take a jumping steps, kind of like it may lose some learning in that case as well, right? So this is the learning rate, what I have defined here. So I'm executing this as well. So after execute, the model has been initialized, loss function we had initialized, optimizer we had initialized. Okay, Now it comes the main part. So this is a training loop. Okay, so here we will start our training. We have defined few arrays here: loss history, accuracy history for each epoch. Like what we have done, we have decided 100 epochs here. May not be needed, maybe lesser as well, right? So you can have 10 epochs or 20 epochs, but I'm using 100 epochs here. Okay, so epochs means the number of iteration the model will go through the entire training data set, right? So model will do one time, two time, three time to adapt the patterns, to learn the patterns out of it, right? So it's going through n number of times to the same data to learn it properly, right? So when you try to learn anything, you keep on going, yeah, you going through that book or any article, right? So to learn that, it's the same thing. So epoch is number of iteration. So here I am just initiating in that training loop for 100 epochs. It's going through the features, input data, labels, the predictions in the data loader. And the first step, it is passing those features in it and predicting some outputs. Okay, this is the first process: putting the features, predicting the outputs. So this variable should be having the house predictions. Now what's doing, it's going to compare the loss. How that's comparing the loss? It's two parameters it is passing: output and labels, right? So these are the predicted outputs and these are the actual outputs. Then it will internally compare the predicted outputs to actual outputs. If the difference is higher, it means it's not correct, loss is high. If it is same or near to same, the loss is low, kind of, right? So this is how it is calculating the loss for the entire batch here. And the third step comes optimizer dot zero grade. So this is just a resetting of gradient. Okay, I'll tell you what what's the use of that gradient here. So it's resetting the gradient. And the another thing, loss dot backward. So it here it computes the gradient. Okay, so what's that gradient is? Okay, gradient is, if you might have studied about gradient in calculus, it's the same gradient, right? So the differentiation. So what we do, uh, we we compute the gradient here to identify like how the loss is going to change with respect to weight. Okay, so that is dy by dx or dl by dw, the loss with respect to weight. It computes the gradient. Okay, so based on that computation, it adjusts the weight to have a lower loss in the next iteration. So see, the uh, goal of model is to by each iteration the loss should go minimum, the accuracy should go high, right? So after each iteration the loss will keep on going lower and accuracy will keep on going higher. Okay, that's how you will say your model have learned everything or it has been trained. So how that happens? So based on the first iteration, it randomly assigns the weights. Okay, it goes through the training and provide some predictions or outputs and compare it. So initially the loss should be higher because the weights are random. Okay, so lot of inaccuracies, the loss should be bigger, I would say. Now the second iteration comes, then it updates the weights based on the loss. Okay, so it will check like what was the loss and how that loss will be minimized after updating the weights. Okay, that's that calculation is that determination is done by your gradient. Okay, so it calculates the gradient and checks how the loss will change with respect to weight if you're updating the weight. So and the next step, it updates the weight based on that, and then the loss goes lower. Again some loss happens, it updates the weights again. Okay, and in the third iteration, it it keeps on going lower. Okay, and ultimately it reaches to the point where the loss is minimum, accuracy is higher. So that's known as gradient descent, guys. Okay, this is a very famous mechanism in neural network that is known as gradient descent. If you want to read more about gradient descent, you can read it from here. So I had tried to explain the gradient descent process in a very user friendly way. You will get the entire idea what that gradient descent is. Okay, so just summarizingly here, just consider in a rough way, you are just, you are at the top of hill, you just need to go down on the, okay, on the plane. So going down is the loss which is minimum. So what you will find the most steepest path, so you can easily go to the bottom towards the zero, right? So that is steepest, like how much steepest path you are choosing, that's the gradient. Okay, so this is how happens in your neural network as well. So it assigns the random weights initially, predicts some values, calculates the loss, and calculate the gradient, how much loss will change with respect to weight, update the weights accordingly, and then do the next iteration. If it is all done correctly, it will expect some lower loss in the next round. Okay, then will it again update the weight based on the next value of gradient, and it will keep on going throughout your number of epochs. Okay, and ultimately at the last epoch, the loss should be minimum, and the accuracy should be higher. And this is the entire internal process how it goes through in neural network. Okay, so that's what we are doing here. So loss dot backward is calculating the gradient, and in the next step it is, it is updating its weight based on the gradient calculated above and creating the loss. So these are the four steps, self-explanatory. So it defines what happens in training, and finally what I'm trying to do, I'm just creating the average loss, average accuracy, putting in the variables, and that's it. So this is the output. Okay, for first epoch, if you see, the loss is 0.29 with accuracy 21. After that, it might have calculated some gradient. Based on that, it might have updated the weights, and then for the second iteration, the loss became 0.26, which was relatively lower. Accuracy was higher. Again, it might have updated some weights based on the calculated gradient. And the third iteration, that was 0.25, and keep on going lower. And the last epoch, it went to 0.20, and accuracy was relatively higher. Okay, so this is just an example, guys. May not be pretty much accurate. You can do much engineering or updating your neural networks or whatever, so you can get the maximum accuracy or minimum loss. But this is a very simple example of feed forward neural network, just to explain the training and validation process to you guys. That's why it is like that. So okay, it is like that. I can initiate the training loop one more time. So if you see, it is going through all that process whatever I had explained. Okay, so it might be calculating some losses and updating the weights. So this is the first epoch for it has done, like it yeah. So first 10 epochs it had done. So for each 10 epochs, I'm printing the value. Okay, out of hundreds. So first 10 epoch, it gave the accuracy of 4 as 0.29. For the second epoch, like second 10 sets out of 100, it the accuracy was 23% and the loss was 0.26. Yeah, and the first one it was 0.29. See, so you will see the loss will keep on decreasing for each iteration of 10 epochs. Yep, it went to 0.24 with 25% of accuracy. So you see the magic, what's going on, right? So for each 10 sets of epoch out of 100, it is, decreasing the loss and increasing the accuracy after updating the weights based on the calculated gradient. Yeah, it's an interesting thing to see or to know, right? So the process is similar as human learns. That's why we say the artificial intelligence. Okay, so that's an ideal metrics. Okay, which is coming up. Yeah, 26% accuracy with 0.21 as a loss. So guys, I'm not going to do the separate inference here. This is just to explain the process, right? So with these metrics, you can understand the model is learning and being ready to predict the housing values, right? Based on the input parameters provided. So simply what you can do, you can save this model and use for your separate inference. Use for your inference. You can load that model, put your random house features in it, and it will give you the value, right? Currently that is learning, and whatever the loss and accuracy figures are coming up, it means the model is learning. Okay, you just need to trust on it. So for the 90 epochs, yeah, 100 epochs done, and eventually we got the accuracy as 27%, which was started from 21% in the first epoch, and the loss went minimum to 0.19 from 0.29. Okay, so this is the training and which has been done for this model, and this is the evaluation I'm doing overall. It's total test, yeah, total test. When we evaluated this model on the testing data set, the total error came as 26%. Okay, so these are some examples I had put. So yeah, so what this is about calculating the error. So how I'm predicting it. So if I'm not here I'm not equating the predicting and I'm not expecting the labels or the actual value and predictive value to be same. So here I'm what I'm saying, if the predicted value is almost near to that, like the difference is only 10% error, right? For example, the value is 3, actual value is 3, and the predicted value is 2.9. So that means that still it's near, right? So I'm considering it as a true or as a correct answer. I'm not saying like it should be 100% 3 and that then it should be the correct. So I'm just giving some flexibility to model here. So if model is near to the actual value, I'm saying it is correct. So that's what I'm doing here. So that was the example is about. So you can see 2.93, 1.54, and another is 3, 2.9, 1.9, 4.1. So it will compare both of these things and will provide what how many are accurate. So ideally it will consider these two values are correct. Okay, and I think these all are correct. So all are pretty near within 10% of error. So all four are correct, right? So if you tweak it something like 2.7 here, so it means that is not under 0.1% of error, then it will consider it's wrong. Okay, so this is what we have done here. We had compared the actual and predicted values. If that is pretty near within 0.1% of error range, I'm considering it as a correct value, and that's it. So yeah, so that is all about the training process of a model. What we do, I'm summarizing it. The first step is collecting some data set, yeah, optimized data set, okay, which you are going to provide to your model for training. Splitting that data set into testing and training, ideal ratio is 80-20. 80% of the data you will use for your training, and 20% of the data you will use for validation after the training is done to check what model has learned. Third thing is training of the model. I had explained the training loop where and the steps, what are those during the training of the model. uh, yeah, so definitely the training dataset needs to be put in the data loader, a class provided in the PyTorch, so it should be suitable to put in the training loop. And what happens in training? It passes the input features, predicted some outputs, predict some outputs. Those outputs are compared with the actual outputs. Predicted outputs are compared with actual outputs to find out the loss. Loss means if the predicted output is equal to actual output, the loss is 0. If there is a big difference, the loss is higher. It's a kind of mistake. Based on the loss, it calculates the gradient, like it checks like how the loss is changing with respect to weight. If that is changing the weight, how loss is decreasing or increasing. Based on that, yeah, so it calculates the gradient for that purpose, and based on that gradient value it updates the weight, change the weight, and during the next iteration it gets some lower loss based on the weight it has updated, right? So using this process the loss keeps on going lower till the end of the last epoch. And that's the training process is about, guys, right? After that we do the validation, and based on the metrics, if those are much accurate, then it means our model is ready. You can download that model or save that model at any location. You can use it for inference, and that's all, how it is done. Okay, so you hope you might have got the idea how the internal mechanism of any neural network, or any neural or any artificial intelligent model or any neural network model, whatever you say. Okay, so that's it, guys. Thank you so much for being with me in this video.